Good morning, class, and welcome to our continuing lectures on sustainable energy technology. In the last class, we started our discussion on comparing the various types of energy storage technologies and the role they can play in integrating renewable energy in the next generation of sustainable energy grids. We were looking at various types of energy storage technologies in terms of their technology types, including electrochemical systems like batteries, electrochemical capacitors, electromechanical systems like compressed air storage, flywheel, chemical systems like hydrogen storage, liquid air energy storage systems, pumped hydro storage systems, different types, and thermal storage systems like chilled water storage, molten salt thermal storage, etc. These are the different energy storage types that can be used to fulfill the various energy storage functions of a modern grid with extensive renewable energy generation systems. Now, let us look at what is the technology maturity level of all of these technology types. So, in this figure, what is being shown is the readiness of a certain energy storage technology in terms of its commercialization. So, the most mature technologies are already at the commercialization stage. They have been successfully commercialized and have been installed in many places. For example, pumped hydro storage. Then peat storage is basically a type of thermal storage in underground systems. As we discussed, you can heat up bricks or high density, high CPCB materials and store heat that way. So, peat storage is basically that type of thermal storage. Underground thermal energy storage is a variation of this thermal storage systems, where instead of digging artificial underground storage systems and storing heavy density materials like bricks there, we are using underground cavern systems containing air or water and is injecting heat in those systems and then extracting that hot water or hot air out at a later time. So, this is called underground thermal energy storage systems, where natural caverns or subterranean water is used to store thermal energy. Cold water storage is also very well mature. As we have discussed, you can chill water during periods of low energy demand and use that chilled water for space cooling applications. Similarly, compressed air energy storage and residential hot water heaters with storage, these are all fairly mature technologies. Okay. See, a lot of them are thermal storage, a few like pumped storage hydro is electricity storage. In the demonstration and deployment phase, we will put lithium based batteries, low speed flywheels, sodium sulfur batteries and molten salt based thermal storage systems. Now there are several lithium based battery systems currently deployed, but they are only recently emerging in the market. So, they have grown significantly. A lot of lithium based large scale storage systems are becoming the norm. So, these are well on the way of technology maturity and commercialization, but still there is significant room to improve. So, there will be more efficient lithium storage batteries, more efficient molten salt batteries. So, they are in the demonstration and deployment phase. So, you are deploying these systems, but still you are continuing to improve the efficiency, the safety and the capacity of these systems. Okay. So, lithium based battery technologies for grid storage applications, molten salt systems, usually these are allied with solar thermal or concentrated solar power systems. Flywheels, these are often used in brakes or in frequency regulation options. These are low speed flywheels. Sodium sulfur batteries, again for grid storage applications. In the research and development phase, we are looking at technologies that have not yet reached the commercialization system and are not yet been deployed on the field for full scale commercial applications. There are prototypes that are there, pilot plants that are there, but still the commercialization has not reached the demonstration and deployment phase. These include things like flow batteries, which are almost near the demonstration and deployment phase. We will see several flow battery installations are currently successfully running. High speed flywheels, we gave an example many classes earlier of certain specific high speed flywheel systems that are under deployment in certain places. So this is still in a R&D phase, but it's almost close to the reasonably demonstration and deployment phase. Beyond that, we have supercapacitors. These are also becoming reasonably mature technologies. So these are beginning to go out into the field into commercialization now. We have discussed supercapacitors in detail in this class. They are a good replacement of batteries in certain applications. So they are beginning to come into the technology market, okay, and going into the demonstration and deployment phase. Below that are technologies that are still not mature enough, and still a lot of R&D needs to be done. This includes superconducting magnetic energy storage. We did not discuss this. Superconductivity is a very high emerging technology. It has a lot of advantages. So one of them is you can use superconducting magnets for energy storage. Okay, these are called SMES, superconducting magnetic energy storage. We did not discuss that. Then adiabatic compressed air energy storage. So this compressed air energy storage here is using natural caverns, right? This is more of a using actual tanks which are well insulated and using those tanks to compress the air. Okay, so this is still in the R&D phase because there is still a lot of development and cost reduction to be done before it can be financially viable and hence can be deployable into the field. Then there is hydrogen. We will discuss. We will spend several classes on about discussing hydrogen. Several pilot scale demonstration projects of hydrogen as energy storage are beginning to come up, but still there is a lot of room for improvement. The costs are still quite high, and so we need a lot of R&D and pilots and field demonstrations before hydrogen can go up this technology curve and towards the demonstration, deployment and full-blown commercialization phase. Similarly, synthetic natural gas. Thermochemical also is a very immature technology right now, and we will not discuss that significantly here. Okay. So this is kind of the curve that we are at. All of these systems that we discussed earlier, these systems and their technology levels. Okay. So here are some examples of various types of energy storage systems and some key places where they are being deployed. So pumped storage hydro is the most mature and most widely deployed technology, as we will discuss. Its location is on the supply side. So where there are large scale grids, it is near those grids, or where there are large scale energy generation systems, it is near those energy storage generation systems that we deploy pumped storage hydro to store excess energy during periods of low demand. The output is of course electricity. Efficiency is around 50 to 85%. When we initially discussed, we said efficiencies are lower. These are more recent installations that are getting better efficiencies out of the system. Initial investment costs. This is basically how much is the initial investment to start the facility going in terms of US dollars per kilowatt hour of stored energy, and this is around 500 to 4,600. So it kind of depends on whether a natural river and a natural hill is available. If neither is available, you have to build those, so that makes it costly. But if you have a natural river or a hill available, that can easily be converted into a PSH facility, so then the investment cost is significantly lower. So again, this is a very important aspect. There isn't a standard price for energy storage, even for a given technology. It's depending on the location, depending on what is available, you can you can have it reasonably cheap and you can have it reasonably costly. Okay, so there is an average and there is a range. Primary application is long-term storage, clearly, because you are storing the water uphill and you are now moving the water back downhill, and it usually takes at least a few hours to do that. Okay, so it's a medium to long-term storage, and of course you can store the water indefinitely uphill. So you can store excess energy for months on end using pumped storage hydro. Okay. Example projects are many. There is a Goldisthal project in Germany, Okinawa Yanbaru seawater pumped storage hydro facility in Japan, which is interesting because it's using seawater rather than river water to store electricity. So that's the kind of innovation of this project. There is a PSH station in Brazil. There are several stations that are coming up in India as well, that have come up in India as well. Then underground thermal energy storage, and here we were discussing that you can store heat or coolness by pumping hot water or cold water in underground aquifers, and you will see that this water retains its heat or its low temperature property for significant amounts of time because the ground is reasonably well insulated. So you can actually store thermal energy quite efficiently if such natural caverns or formations are available. Okay. Again, the location is on supply side. That's where energy generation is happening. Output here is thermal output. So the hot water that is produced or the cold water that is being generated is being kept, and it is heat transfer that is the primary goal of these kinds of systems. Efficiency is 50 to 90%. Initial investment cost is high because you have to dig these underground pipes, properly seal them, have a reasonably good facility. So you are getting the initial investment cost is significant, 3,400 to 4,500 US dollars per kilowatt. And this is again reasonably long-term storage. So unlike most other thermal storage systems, you can actually store heat or coolness for quite a long time in underground thermal energy storage facilities. Examples are Drake Landing Solar Community in Canada, Arcasius University Hospital and Nydalen Industry Park in Norway, etc. Okay. Then you have compressed air energy storage. We have discussed this significantly in our classes. Again, supply side, output is electricity, efficiency is 27 to 40%. So efficiency of compressed air energy storage is lower than pumped storage hydro, as you would expect, because air compression is energy, it takes a lot more energy than pumping water. Okay, so the efficiency takes a hit. Initial investment cost is 500 to 1500. Again, usually this requires a natural cavern system. So, but you still have to drill the holes and the pipes to put the air there. So you have a reasonably high investment cost once more. This can be used for long-term storage as well as arbitrage. So here arbitrage is if you have a gas power plant, for example, and you can generate more electricity than and the demand is low at a certain period of time, and you are using the excess energy of the compressors to pump excess air into your cavern. Then when the demand is high, you are pushing that air out and you are generating more electricity, and you are selling that electricity at the high price at this high demand point, and hence getting a profit out of it. So this is a kind of an arbitrage storage solution as well for the gas power plants. It's a reasonably long-term storage. You can store compressed energy in underground caverns for periods of days, so it's long-term. Examples include McIntosh in Alabama in United States, Huntorf in Germany. You don't have to remember these names, just a few examples. If you are interested, you can look into these applications or how they have done these things there. Pit storage. This is basically you are using insulated tanks or pits, putting bricks or earthen mounds which are heated by passing hot air or hot water through them, and this heat is then later used for your space heating needs when the demand is high. Okay, so that's the pit storage technology that we have discussed. So supply is again on the supply side. Output is thermal. Efficiency is 50 to 90%. Of course, this is the Time scales are of course less, 6 to 8 hours maximum. Initial investment cost is significantly low, 100 to 300 US dollars per kilowatt, because basically you are using very cheap thermal brick materials, and the cost is only the insulation and the piping through them. Okay, these are medium temperature applications, so you are using this hot air in the building systems. Example is a Marstall district heating system in Denmark. So a district heating system where you are piping hot air and hot water to the various houses in a district, and you have a centralized pit storage system which is through which air heated during times of low demand is heating up that brick system, and then during periods of high demand, air is flown through this hot brick, piped through this hot brick, and the air is getting heated up. Okay, and this hot air or hot water is being transmitted for space heating needs. Then you have molten salt systems. Obviously, these are primarily associated with nuclear power plants or concentrated solar power plants. Again, it's supply side because these are associated with power plants which are generating the electricity. So that is why it's supply side. Output is thermal, efficiency is 40 to 93%. Again, depending on the installation, the efficiency will change. The initial investment cost is $400 to $700 per kilowatt. This is primary application is high temperature application. So you are using the molten salt, heating it at very high temperatures, and so if you want very high temperatures in some industrial systems, then molten salt can be used, or you can use that molten salt to generate electricity. So two applications, either high temperature or using that high temperature to generate electricity. And a typical example is a concentrated solar power plant. So it's a Gema Solar concentrated solar power plant in Spain is where molten salt storage systems are used. Then you have batteries. This is very flexible. You can have it on the supply side where power generation is happening to store energy, or on the demand side where an user is storing energy during periods of low electricity cost, and then using that energy at a later date during periods of high electricity cost instead of sourcing it from the grid. It can also use a demand side in, for example, in a electric vehicle charging station or within an electric vehicle system itself. So that's a user demand. So it's a demand side system. Output is electricity, efficiency is 75% to 95%. So lithium ion batteries are reasonably efficient. Initial investment cost is $300 to $3,500 per kilowatt. Again, it is kind of dependent on whether you are using a demand side or supply side. If it is supply side, you have to make very large installations to store electricity. So that increases the investment cost. On the demand side, it can be as small as a simple battery pack in a car, or a battery pack that is used in a distributed system. You are storing the energy and you using that energy in a remote location. So you can have lower investment cost under those conditions. Primary application is distributed or off-grid storage, as we discussed, short-term storage, and of course it is also being now used in EV cars to power transportation systems. Okay. Example projects include sodium sulfur batteries. So there are various types of batteries, of course. So sodium sulfur, we have discussed this. It's kind of the molten battery system, and this kind of batteries are very good in conjunction with grids to store electricity in the grids to improve the quality of the grid electricity and decrease the intermittency of renewable power plants. Examples are Presidio in Texas, US, and Rokasho Futamata project in Japan. Then you have a vanadium redox flow batteries. We have not discussed redox flow batteries in detail. It's a kind of a flow battery that can be run indefinitely. But again, there are several centers in Japan where these kinds of batteries are used. Then the traditional lead acid battery. There is a wind storage application in note trees in United States where this kind of lead acid batteries are used. Then you have lithium ion batteries, multiple places in United States. Then there is something called a lithium polymer battery that is present in France. So battery storage systems are present in many places, and we will see in the next few slides that a lot of growth has happened in battery-based energy storage systems for grid applications throughout the world. Then you have thermochemical storage systems. These are still in very R&D phase, so there are very few systems. These are also connected with concentrated solar plants. Output is thermal, efficiency is quite high, 80 to 99%. Investment costs are quite large, $1,000 to $3,000 per kilowatt hour. Primary is low, medium and high temperature applications. So all the temperature applications, these thermochemical systems can work. Then you have chemical storage, hydrogen storage, storing energy in terms of hydrogen gas. Okay, we will discuss this in detail in the next few classes. This is also quite flexible. It can be on the supply side. You are using the excess electricity to electrolyze water and to generate hydrogen and storing that hydrogen beside a renewable power plant, a renewable energy farm like a wind farm or a solar farm, and then that hydrogen can be put into the grid to generate either electricity or thermal energy. Okay, so it can do both. So here output need not be electrical actually. If you have a fuel cell system, yes, it's electrical, but you can also move this hydrogen directly into furnaces, then it can be thermal. Okay. Efficiencies are low. So this is why it's in the R&D phase. 22% to 50% is the efficiency you are getting in hydrogen storage systems. Initial investment costs are moderate, $500 to $750 per kilowatt hour. The costs are primary for the electrolyzer system that is used to generate the hydrogen and the hydrogen storage systems. Primary application is long-term storage. You can store the hydrogen for a very long time, so you can use that as a long-term energy storage option. Examples are Utsira hydrogen project in Norway, energy complementary systems in Germany. Okay, so this is hydrogen storage. Then we come to flywheels. We have discussed flywheels, and flywheels are present in many places. It can be used in the as we discussed in trains. It can be used for grid quality improvement. So those voltage quality and these applications that we discussed previously. Frequency regulation and voltage support. Flywheels are very good for these kinds of applications which are looking at the power quality. Okay. Output is electricity, efficiencies are very high, 90 to 95%. Initial investment costs are reasonably low, 130 to 500 kilowatts. It's basically the flywheel itself and the setup in which this flywheel is moving. It's short-term storage, so primarily again used for improving of the electricity quality in terms of reducing voltage fluctuations, power fluctuations, phase fluctuations, etc. Okay. There is a PGM project in the United States. We also give an example of a project in Germany which is using a flywheel system. Supercapacitors, also very similar, short-term storage, used for improving the quality of the electricity in the grid. Initial investment costs very similar, and there are hybrid electric vehicles where supercapacitors are used for regenerative braking applications. So, and also in grid systems. Okay. So flywheels and supercapacitors are very similar to each other. In terms of the renewable grid, they are used for power quality maintenance, and in transportation they are often used in regenerative braking applications. Then we have discussed ice storage. This is on the demand side primarily. So you have a building system, you want to cool it, so you are having an ice storage facility. You are using electricity and a chiller facility to create the ice at periods of low demand and then utilizing that ice to cool the buildings. Output is thermal, efficiency is 75 to 90%. Initial investment costs are quite high, $6,000 to $15,000 per kilowatt because of the storage facility involved and the costs for developing a large enough storage facility. Used for low temperature applications. There are several projects in Japan and in China that are there using this ice storage facility. Very good for hot countries as well. Hot water storage, residential, very clear example of a demand side case with thermal energy. Efficiency is high. Medium temperature applications. It can be used for peak demand reduction and TCS systems in US. Cold water storage, again very similar kind of thing, so I am not going over this. We just discussed ice storage for an airport and cold water storage also in similar cases. So very similar ideas. Okay, so you are using the cold water storage in Shanghai International Airport just as we used in the airport in Dallas in Texas. Very similar systems. So this kind of gives us an overview of the basic energy storage systems that are existing and some of the applications. So here we can discuss the current status of these various energy storage facilities, technologies. So here is the rated power in gigawatts that these facilities can actually deliver. Okay, how much power these facilities can deliver under rated conditions, about what is installed today. So here today is not today, it's mid 2017 data that I got. So the recent data I do not have available. It will have changed to some extent because this is a fast growing technology, but the basic trends should be the same. And you can see that the pumped hydro storage is by far the largest energy storage systems in the world, with 160 gigawatts of rated power in 2017, and every other type of storage is small compared to pumped hydro. It's the most mature and the most widely deployed large capacity storage system. After that, you have thermal storage, electrochemical storage, which is batteries, and electromechanical storage like flywheels and compressed air storage systems. Okay. So pumped hydro, the largest by far. Okay. Among the rest, so if you look at thermal storage, electrochemical storage and electromechanical storage and see what fraction among these is from different technologies, then for thermal storage, molten salt thermal storage is the most dominant technology type associated with CSP systems, nuclear power plants, etc. Okay. Then you have other things like other thermal storage technologies, then chilled water storage, hot thermal storage, etc. Electrochemical storage is basically batteries, and here lithium ion battery is the dominant technology. As we have said, lithium ion battery is being used everywhere. It has very good efficiency and specific power in terms of weight ratios, so it's the dominant technology. There are other batteries also available. Sodium based batteries are also quite popular, sodium based batteries and sodium sulfur batteries. There is electrochemical capacitors that are also reasonably popular. So these are the main types, and lead acid battery is also there. Among electromechanical, you have only two, compressed air and flywheel. Flywheel is the largest, followed by compressed air. So today I will stop here. In the next class, we will see the growth of these technologies over the current decade and how these technologies have grown over a certain period of time. Okay. Thank you for listening, and we will see you again in the next class, and have a good day.